What specific problem does the new method, meta-reinforcement fine-tuning, MRT, solve related to leveraging long-term reasoning in LLMs?
Meta-reinforcement fine-tuning, MRT, addresses the inefficiencies in how current LLMs utilize test-time compute, particularly in generating long reasoning chains. Traditional outcome-reward reinforcement learning fails to ensure that LLMs make steady progress towards discovering correct answers, especially on harder problems, leading to suboptimal token usage. MRT introduces a dense reward bonus that incentivizes models to optimize for cumulative regret, promoting a balance between exploration and exploitation during reasoning. This approach allows LLMs to effectively segment their output into episodes, enabling them to explore multiple strategies and verify prior answers, ultimately improving both accuracy and token efficiency. By training LLMs to minimize regret, MRT ensures that they can adaptively leverage longer reasoning processes without prematurely committing to incorrect solutions.
How does the proposed method, MRT, work? Illustrate step-by-step the process of training and deployment in this context, including the formulation of cumulative regret.
The proposed method, meta-reinforcement fine-tuning, MRT, works by optimizing the performance of large language models, LLMs, in utilizing test-time compute effectively. The training process begins by segmenting the output stream of the LLM into episodes, which allows the model to explore different strategies and verify previous answers. During training, MRT incorporates a dense reward bonus that measures the progress made by the model in terms of likelihood of arriving at the correct answer, thus optimizing for cumulative regret, which quantifies the difference between the model's performance and an optimal comparator. This cumulative regret is minimized by ensuring that each episode contributes positively to the overall progress, allowing the model to balance exploration and exploitation effectively. Upon deployment, the trained LLM can adaptively utilize a larger token budget, making steady progress towards the correct solution while being agnostic to the specific budget used during training, thereby enhancing both efficiency and accuracy.
Can you provide a simple yet illustrative example that demonstrates how MRT functions in practice, particularly how it generates and evaluates iterations on a math problem?
In practice, the meta-reinforcement fine-tuning, MRT paradigm operates by segmenting the output of a language model into episodes, which allows for iterative reasoning on a math problem. For instance, when tackling a math proof question, MRT would generate a sequence of reasoning steps enclosed within less than think greater than markers. Each episode represents a distinct attempt at solving the problem, where the model can explore different strategies or verify previous steps. After generating these episodes, MRT evaluates the progress made by measuring the likelihood of arriving at the correct answer after each episode, using a meta-prover policy that assesses the cumulative regret. This process ensures that the model not only seeks the final answer, but also learns from each iteration, optimizing its use of tokens and improving overall accuracy, as evidenced by the empirical results showing significant performance gains over traditional outcome-reward methods.
What are the main theoretical and practical benefits of using MRT over traditional outcome-reward RL approaches, especially in terms of efficiency and accuracy in reasoning tasks?
The main theoretical benefit of using meta-reinforcement fine-tuning, MRT, over traditional outcome-reward RL approaches lies in its focus on minimizing cumulative regret, which allows the model to make steady progress across episodes rather than merely achieving a correct final answer. This approach encourages exploration of multiple strategies, leading to a more systematic discovery of solutions for complex problems. Practically, MRT has demonstrated significant improvements in both efficiency and accuracy. For instance, it achieves state-of-the-art results with a 2 to 3x relative performance improvement compared to standard outcome-reward RL, while also enhancing token efficiency by 1.5 to 5x. Additionally, MRT maintains or improves accuracy even when reducing output length, which is a critical advantage over traditional methods that often sacrifice accuracy for brevity. Overall, MRT's design enables LLMs to effectively utilize test time compute, making it a more robust solution for reasoning tasks.
How was the method validated or tested in the experiments, specifically regarding the datasets used, benchmarks for performance, and metrics for evaluating efficacy?
The method, Meta-Reinforcement Fine-Tuning, MRT, was validated through experiments on multiple math reasoning datasets, including AMY 2024, AMY 2025, AMC 2023, and Math 500. The performance of MRT was benchmarked against Standard Outcome Reward Reinforcement Learning, GRPO, and other methods, with a focus on pass-at-one accuracy as the primary metric for evaluating efficacy. Additionally, token efficiency was assessed by comparing the accuracy achieved per token used, demonstrating that MRT required significantly fewer tokens to achieve comparable or improved performance relative to baseline models. The experiments involved fine-tuning base models like DeepSeek R1 Distill Qwen 1, 5B and DEEPSCALER1, 5B preview on a dataset of 10,000 randomly sampled problem solution pairs from Numina Math, and the results indicated that MRT consistently outperformed traditional methods in both accuracy and efficiency. Overall, the evaluation metrics included cumulative regret, pass-at-one accuracy, and token efficiency, providing a comprehensive assessment of MRT's effectiveness in optimizing test time compute.
What limitations or drawbacks of MRT were noted in the paper, particularly concerning its performance and the trade-offs made in the design of the method?
The paper notes several limitations and drawbacks of the Meta-Reinforcement Fine-Tuning, MRT method. Firstly, while MRT improves performance and token efficiency, it does not guarantee optimal performance across all problem types, particularly when the model encounters problems that require more episodes than it was trained on, leading to inconsistent progress. Additionally, the results indicate that the cumulative regret may still grow with the number of episodes, suggesting that MRT does not always ensure meaningful progress in every scenario. Furthermore, the paper highlights that while MRT achieves state-of-the-art results, the absolute performance gains are relatively small due to the models being fine-tuned on already distilled or RL-trained base models, which may limit the potential for further improvements. Lastly, the design of MRT, which emphasizes a balance between exploration and exploitation, may inadvertently lead to inefficiencies in simpler problems where a more straightforward approach could suffice.